Dear students, now we shall proceed to the part 2 of electrochemistry. In the previous lessons, we have learned that the electrolytic processes, that is the conductivity, conductances, all these and relations between them, all this, and here we shall deal with the energy aspect of electrochemistry, where a chemical energy is converted into electrical energy in electrochemical cells or in galvanic cells. So, before going in detail, again we have to read some terminologies used in the subject, that is first of all the electrolysis. So, it is a one word, and but it has two components. Electro stands for electricity or electric charge, lysis stands for breaking, that is breaking caused by electricity. In fact, when we pass electricity through a solution suitably connected through a DC voltage, DC power supply, then the ions tend to move towards the electrodes, that the end connected to. So, already, so I will make a diagram here. So, of an electrolytic cell. So, in the previous class also I have made a diagram of an electrolytic cell. These are the electrodes, or we can say the metal strips, So, this is, and this is in fact an anode, and this is a cathode. They have been connected externally to show, and that is a key here. So, this is a positive end and this is a negative end, and this is the DC supply and this is the key, and here it is a solution is there. So, this solution is called electrolyte. So, when the key is made on, the charge flow through the solution, and the ions inside the solution, they move towards the respective electrodes. In fact, the cations move towards the anode and the anions move towards the anions move towards the anode and cations move towards the cathode, and they get discharged, ions get discharged. So, suppose and that means oxidation takes place at anode and reduction occurs at cathode. So, this is a general electrolytic process with all with the device called the electrolytic cell. The device is called an electrolytic cell. To understand better regarding the functioning of the electrolytic cell, we shall cite examples where we are expecting the products of the electrolysis. The products of electrolysis, That means, during electrolysis, what products we are expecting to get are the electrodes. So, this depends upon two factors. One is the discharge potential, another is electrode material. So, discharge potential means what? The minimum potential that a particular kind of ion, that is cation or anion, they require to reach the particular electrode, the discharge potential. That means, the ions carry some charge, either positive or negative. So, when they reach the electrode, they lose their charges. So, either by receiving electron, if it is a cation, it receives electron, and here the reduction takes place. If it is an anion, it gives up electron, and so that's where they discharged. So, that is known as discharge potential. Then another thing is that electrode material. So, how electrode material affects the process of electrolysis? That if the electrode material is inert, like your platinum is used, platinum electrode, then it is an inert material. So, it does not interfere in the process of electrolysis. But other metals, the other metals, suppose we use mercury and other metals, there is sometimes. So, we shall cite examples to understand it better. So, they will interfere in the process of electrolysis and the products will accordingly change. And so, let us take the example first, the electrolysis of lead bromide. Lead bromide, you know, lead bromide, this is lead bromide. So, it will ionize as divalent lead, and this will so this is this. So, what will happen? There will be a cathodic reaction and there is an anodic reaction. So, at anode, so what happened? Bromide plus electron, this will happen. So, what will happen? This is here, you see anode, here oxidation occurs. So, how can you say it is an oxidation? Oxidation, you know, this is loss of electron, it is okay. And another way we can say oxidation is increase in oxidation number. See here oxidation number is -1 and here oxidation number is 0. And this is a primary change, we call it a primary change. Next what happens? Then bromine atoms, they combine to give rise to bromine, This is a secondary change. This is a secondary change. And at cathode, similarly, at cathode, this Pp2 plus, they obtain 2 electrons, Pb is deposited, cathode. So, the ultimate outcome or the ultimate result or the products of electrolysis. So, while we electrolyze molten lead bromide, what we obtain? We get bromine gas liberated at anode and lead deposited on the surface of cathode, and this is using platinum electrode. This is using platinum electrode. So, this is the result. So, now we shall now we shall cite one more example. So, that is electrolysis of brine. So, what is brine? Brine is a dilute solution of sodium chloride, that is called brine. So, first we shall make it with platinum electrode. So, here sodium chloride in a, so it will ionize as sodium ion and chloride ion, and water will ionize as H plus plus OH minus. So, here you see the difference between. So, here I have put a single headed arrow, here there is 2, that means half arrows pointing to different directions. So, what is happening? In fact, this is a completely ionized salt and this is very feebly ionized, almost we say we can call it is not ionized. So, there will be, so there are 2 cations and 2 anions. So, there will be a competition between the 2 cations to be discharged at cathode, and there will be competition between the 2 anions to be discharged at anode. So, the winner will be the ion having lower discharge potential. So, this is according to the preferential discharge theory. There is a theory called the preferential discharge theory. According to this theory, ions requiring less potential to get discharge will be preferred over the other. That is thing. So, here in fact, among cations this will be the winner and among anion this will be the winner. So, there will be an anode reaction. So, anode reaction is that Cl minus will Cl plus electron. This is in fact your oxidation occurs, at anode oxidation occurs, already you have mentioned it, and this chlorine in a secondary process will give rise to chlorine gas. And at cathode we are expecting H plus to move. In fact, H plus will not move since water is feebly ionized. So, in the ionized in the equation water, it will give rise to half H2 plus OH minus plus here in 1 electron will be added up. So, this is the reaction. So, this is in fact the reduction reaction. A reduction reaction, that means it liberates hydrogen at anode. So, what is the outcome? What is the result of electrolysis? Result of electrolysis. So, you can the question you can ask question in the examination, what happens when sodium chloride solution or brine is electrolyzed. So, you will write these equations and lastly you have to write down the result. What is the result? Result is, what is result? That chlorine is liberated at anode 1. Number 2, what is the result? Hydrogen is liberated at cathode. Number 3, the solution, that is the final solution after electrolysis, the solution becomes alkaline. Alkaline means its pH become greater than 7. The solution becomes alkaline. That means NaOH is left behind. So, this is the process in which sodium hydroxide is prepared. So, already we have mentioned in the first class. So, that is how the electrolytic cell is used to prepare sodium hydroxide, or this is known as caustic soda. Sodium hydroxide is otherwise known as caustic soda. So, instead of using, so again this is using platinum electrode. So, if I will use mercury electrode in place mercury electrode, so there will be change in the reaction. In place of H plus, the sodium will prefer to move towards the sodium ion will move towards cathode. So, that will have at cathode, what will happen? Sodium and Hg. So, they will form an amalgam. Any metal combines with mercury to form an alloy is called an amalgam. So, here an amalgam is formed. So, this is how the products are changed by using the different electrodes. So, and there will be so many numerous examples you can cite. You can take the examples of electrolysis of copper sulphate solution, silver nitrate solution, and so and so. So, these are the things. So, next we shall proceed to the two important laws of electrolysis. They are called the laws of electrolysis. Laws of electrolysis. So, first of all we shall go Faraday's first law. So, Faraday in fact gave a quantitative idea regarding the amount of electric charge passed during electrolysis and the amount of substance produced as the products. So, they give the quantitative idea. So, if what are the implications of Faraday's laws? So, it gives a quantitative aspect of the charge passed and the amount of substance produced. Produced means either liberated as a gas or deposited as a metal. So, that is what the Faraday's first law. You all get the statement of Faraday's laws in books. It says that quantity of charge passed through an electrolytic solution during electrolysis is proportional to the amount of substance produced. So, mathematically, so the mathematical form is very simple. W is proportional to Q. So, W represents the amount of substance produced as a product of electrolysis, and Q is the quantity of charge. Q is the quantity of charge. If I will remove the proportionality constant, so I will add a proportionality constant here Z. Remove the proportionality, I will add a proportionality constant. So, this will be Z into Q. So, Z is a constant. Z is called electrochemical equivalent. Electrochemical equivalent, or very simply ECE, electrochemical equivalent of the electrode material of the electrode, EC. Then this is equal to, you can I into, Z will be there, Z multiplied with I into T. So, this is the I is equal to current in ampere current in ampere and T is equal to time of passage of current, time of passage of the charge or the current, whatever. So, this is the mathematical form of this. So, we can define from this equation, we can define what is Z, this is C. That is, if we put I is equal to 1 ampere and T is equal to 1 second, then W will be equal to Z. So, in this condition, so when that means, so when 1 ampere of current is passed for 1 second through an electrolytic solution, the amount of substance formed is called the electrochemical equivalent of that electrode. So, we can define in that way. So, or we can say when 1 coulomb of charge is passed through an electrolytic solution, the amount of substance produced is called electrochemical equivalent. So, this is a very significant term. So, we can have a quantitative relationship between the electrochemical equivalent and the equivalent mass. So, we will get it after knowing the second law of Faraday. Now, we shall learn about the Faraday's second law. What second law says? This is Faraday's second law of electrolysis. So, there is a statement also like all the laws. So, there is a statement for the Faraday's second law. It says that when the same quantity of charge is passed through different electrolytes connected in series, then the amounts of substance produced is proportional to the equivalent masses of the substances, respective substances, that equivalent mass. So, that means suppose we are having 3 electrolytic solution. Suppose one is a copper sulphate solution, another is a dilute sulfuric acid solution, and another is a silver nitrate solution. So, according to these 2-3 solutions, according to this, so the amount of substance W copper is proportional to the equivalent mass of copper W. Here hydrogen suppose will be produced, it will proportional to equivalent mass of hydrogen, and so on. So, W silver produced is proportional to number of equivalents of silver, equivalent masses and number of equivalent. That means, same quantity of charge will produce a definite quantity of substance at the electrodes. So, we can also put it in a mathematical form. So, how? Suppose W1 is for electrolyte 1, it is proportional to E1, and W2 is proportional to E2. They are equivalent masses, respective equivalent masses of the substance produced. Then to eliminate the proportionality constant, we can we can divide the two. So, we will have W1 by W2 will be equal to E1 by E2. Now, what does it imply? It implies W1 by E1 is equal to W2 by E2. That means, the ratio W by E, it represents what? Number of equivalents. It represents number of equivalents of a particular substance. That is the mass of the substance, suppose in gram, and divided by the gram equivalent mass. So, the 2 gram in the denominator and numerator, they are cancelled. So, it will come out to a number, that is number of equivalents. For example, I can say, suppose I can say, so suppose I will say 27 gram of aluminum is equal to dash number of equivalents, dash number of equivalents. So, I will make it clear. So, equivalent mass of aluminum is its atomic mass divided by valency, that is 3. So, it will be 9. So, the result will be 27 divided by 9. So, this will equal 3. So, that is 27 gram aluminum represents 3 equivalents of aluminum. So, this is number of equivalent. That means, what we find that when same quantity of charge is passed through 2 electrolytes 1 and 2, the number of equivalents produced at the electrodes, they are same, they are equal. So, this is the general outcome of the Faraday's second law. So, we shall generalize it in a more common way. So, that is Faraday's found that when 1 mole of charge, when 1 mole of electronic charge, this is when 1 mole of electronic charge is passed, then 1 gram equivalent of substance is produced. This is the general outcome of the Faraday's second law, when 1 mole of charge. So, let us know what do we mean by this 1 mole of electronic charge. So, this is in fact a constant that is known as Faraday's constant. So, what is that? So, 1 mole of charge, electronic charge, that means this is 6.02 into 10 to the power 23, this stands for 1 mole, and the charge of electron is 1.6 in 10 to the minus 19. So, this will be coulomb. So, and this is approximately equal to 96,500 coulomb. C, we write it C, right, the coulomb, C stands for coulomb, and this is called 1 Faraday, 1 Faraday of charge, or we call it Faraday constant, Faraday constant. This is 1 Faraday, or and it is written as 1F, very simply it is written as 1F. So, when 1F, 1 Faraday of charge is passed through any electrolytic solution, we will find that it will produce 1 gram equivalent of the substance. So, now we shall apply this principle to these small equations of electrode processes, oxidation reduction. Suppose I will take the example of sodium. That means, so here 1 mole of charge, that means 1 electron is involved, sorry, 1 mole of electron is involved. So, it will produce 23 gram. This is the quantitative aspect of electrolysis I am now talking about the quantity. So, when 1 mole of charge or 1 farad of electricity is passed, we get 23 gram of sodium. So, this is 1 Faraday. Suppose I will take copper. So, I will get copper here. So, here, so 2 Faraday of charge will produce 63.5 gram of copper, 63.5 gram of copper. See, if I will reduce it to 1 Faraday, so this implies if I will use 1 Faraday in place of 2 Faraday, so I will get half of this. So, this will be 31.75 gram. Similarly, for aluminum, there will be 3 moles of charge aluminum. So, this is 3 Faraday will produce 27 gram. 1 Faraday will produce your 9 gram. So, here you see 9 gram, this is 31.7. So, these are all the equivalent masses of the respective substances we are obtaining at the electrodes. So, that means, so this proves that when same quantity of charge is passed through different electrolytes, so we get this. So, now, so we have already defined the term electrochemical equivalent. So, we give a mathematical formulation to that now. So, what is that? So, 96,500 coulomb produces 1 gram equivalent of substance. Just this arrow this space stands for the amount of substance produced by this charge. So, this implies 1 coulomb will produce how much? 1 divided by 96,500 gram equivalent of substance. So, now I can say that, so this is equal to equivalent mass divided by 96,500 gram. So, I pick this equivalent here in place of 1. So, equivalent mass. So, this is equal to Z. This is equal. So, electrochemical equivalent is the ratio of this what equivalent mass of the substance divided by this. So, this is what the quantitative aspect we learn from the laws. So, now we shall try to solve the problems based on the quantitative aspects of the Faraday's laws. So, here you see question number 1 asks that how much copper is deposited on cathode if a current of 3 ampere. So, here current is given 3 ampere is passed through an aqueous solution of copper sulphate for 15 minutes, T is equal to 15 minutes. So, the multiplication of the two, so you can use directly the formula W is equal to ZIT. So, here Z is equal to E divided by 96,500 into I into T. So, if I will this is equivalent mass of copper is 31.75, this is 96,500, I is your 3 and T is your 15 minutes. So, multiply with 60, this is seconds. So, this will be the value, this is the answer. This will, if you will simplify this is the answer. So, this is the answer from using your first law of Faraday. So, we can get the same result by using the second law also. How we can do it? You see this product 3 into 50 into 60, this is coulomb, this coulomb. Now, the charge we are using for production of copper is this charge, but we know that we already know from second law that 96,500 coulomb produce what amount? 31.75 gram of copper. We know this, we know. This is from this part I have done, this is part on first law, directly from first law, and this is from using the second law. 96,500 coulomb produce 31.75 gram copper. So, this amount of charge will produce how much? 31.75 divided by 96,500 into 3 into 15 into 60 gram. Here also this is gram. You see both are same, both are same. So, we can get the same result out of this, the same quantitative results can be obtained either from using first law or second law. Okay, students, we are talking about the quantitative aspects of the laws of electrolysis, in fact the Faraday's laws of electrolysis. So, through solving problems, so we can better understand this. So, now already we have solved one problem. So, now let us move to one more. So, it is in the screen. So, the problem says calculate the number of electrons required to deposit 40.5 gram of aluminum. So, here you see there is, it is not asked charge, how much charge is not been asked, it is asked how many electrons are required. So, this is the reduction equation, this is the reduction equation showing the formation of aluminum. So, according to this equation, here 3 moles of electron produce your 27 gram of aluminum. So, we can say that 3 into 6.02 into 10 to the 23 number of electrons produce 27 gram of aluminum. As we can make it in another way. So, 27 gram of aluminum is deposited by passing 3 into 6.02 and 1023 number of electrons. So, this implies your 40.5 gram of aluminum will deposit how many number of electrons. So, actually the number of electrons give rise to the amount of charge or the quantity of charge passed. So, therefore, we can make such similarity also. So, this will be 3 into 6.02 into 10 to 23 divided by 27 into 40.5. So, this is in fact this is 9, this is 9, this will come out to be 9 and this will be 3.5, this will come out to be 3.5 and the multiplication of this 3.5 into 6. So, this will be around if you will take only 6, so this will be 210 into 223. 6 into 3.5, this will be 21 into 10. This is 21, this will be the number of electrons, 21 into 10 to 23 number of electrons. So, this is the answer. So, this number of electrons will produce 40.5 gram of aluminum during electrolysis. So, if you will go on solving such problems, so you can better understand the quantitative aspects, and you can have better hold on the understanding. So, now let us move to the most important aspect of the subject, that is electrochemical cells or the galvanic cells, or we may call it the voltaic cells. So, electrochemical cells, already in the beginning we have been told that electrochemical cells, these are the devices which convert the chemical energy into electrical energy, and in fact the free energy decrease of the processes occurring at the electrodes are the driving force of the production of electricity. So, to better understand this, let us draw a general type of galvanic cell. So, we shall take the example of a Daniell cell. We shall take the example of a Daniell cell to understand the working, construction and function of the cell. So, what is a Daniell cell? Here you see. So, here having two compartments, we call them half cells. These are the metal strips. These are the metal strips. So, this is a voltmeter is here, and is a key is here. This is the, and here this is zinc sulfate aqueous, and this is copper sulfate aqueous, that means copper sulfate solution, and this is a zinc rod or zinc strip, zinc electrode, and these are copper electrodes. So, what, and there so this part, so there will be salt bridge in place of this electrode here, there will be a salt bridge, here. So, this is in fact a salt bridge. So, how we construct this electrochemical cell? We dipped a zinc rod or zinc strip into a solution of zinc sulfate, and a copper strip into a solution of copper sulfate, and they are externally connected by a conducting wire, where a voltmeter is there to measure the amount of current generated, and there is a key here to start the cell, and here internally they are connected by a salt bridge. So, I will tell you what is a salt bridge. Salt bridge, in fact, it contains a typical electrolyte like potassium chloride and or potassium nitrate or ammonium nitrate, so and so, in an agar medium. So, it has a specific role to play. Basically, it maintains electrical neutrality in the two compartments, and also they completes the circuit. So, these are the two basic functions that a salt bridge performs. So, one, it maintains electrical neutrality in this half cell and in this half cell also. This is called this left part is called left hand half cell, or this is an oxidation half cell, and this is called the right hand or reduction half cell. So, depending upon the process going on at the respective electrodes, so the name are also accordingly, that is a left hand half cell, this is a right hand half cell. So, this is how a galvanic cell is. This is the general form of a galvanic cell, where the left hand half cell or anodic compartment is in the left, and this is also convention, and always the left hand compartment is made anode and the right one is made cathode in the blackboard. So this is a Daniell cell. So I can designate this cell like this: zinc solid in contact with zinc sulphate aqueous. This double line represents the salt bridge, and this is copper sulphate aqueous copper solid. So if you will move from left to right, so you can get everything. You see here in the extreme left, this is zinc, you see this is zinc, then and it is in contact with zinc sulphate, and here this is salt bridge, again there is a copper sulphate and copper. So this is the cell notation, we call it, this is the cell notation, cell notation. So now we shall focus on its working. So when key is made on, what happens? Zinc starts to decay. This is very important. Zinc starts to decay. That means zinc goes into the solution as ions, and at the same time copper 2 plus in the solution, they receive these electrons and they get deposited on this copper strip. So what happens when the switch is made on? The copper, the zinc goes into the solution as zinc ion and get oxidized, while the copper ions receive the electrons and get reduced to copper and get deposited on the copper strip. So this is the working, and we can put it in this way. So the lost electron here, these electrons that is been come out, so they move in this way. So the electrons movement is like this, and the current, you know, the conventional current always moves opposite to the flow of electrons. So that's why this is the motion of current. This is I and this current. So there are many times the questions are asked, what is the direction of flow of electrons and current in a galvanic cell? So galvanic cell, the current flows from cathode to anode, while electrons flows from anode to cathode in external circuit. That means in this way, in that way. So this is how this it performs. So now we shall know the other outcome of this operation. So we can test the reversible nature of this galvanic cell. So how can you test it? That means whether it will be a reversible cell or not. So it is known as reversibility in thermodynamic sense. So in order to test the reversibility of any electrochemical cell, what we shall do? So we shall externally connect this cell with an external EMF. So if in fact in standard condition, the voltage will be here 1.10 volt in standard condition, that this is known as E0 cell. Standard EMF of the cell, of the Daniell cell, is 1.10 volt. This is, so this amount of standard condition means the concentration of zinc sulphate will be 1 molar, and that of copper sulphate will be also 1 molar. So all these zinc and copper, they will be in the pure form, and the temperature will be temperature will be 298 Kelvin. So in this condition, this particular Daniell cell produces 1.10 volt of electricity. So in order to test its reversibility, what we will do? We shall externally connect another EMF. So if we will increase the external EMF, we will find that the cell reaction will altogether alter. So it will move in opposite direction. So the electron motion and the current, they will reverse their directions. And if when the external EMF is less than 1.10 volt, so that as usual the conventional current and electron will flow. And when they will be same, the E0 cell and E external, they will same. E0 cell and E external, they will same. So a state of equilibrium will come, and all the process will stop. So if this happens, then we can say that this particular Daniell cell is a reversible cell. So this is the test of reversibility, and I explained it, the working of the construction and working of the cell. Then we shall move to another important term, that is called the electrode potential. Electrode, this is a very important term. So, like this your galvanic cell, electrode potential is also important. Potential stands for the tendency, that means for tendency for some change, that is called the potential. So, electrode potential, let us imagine a metal is in contact with the solution of its own ion in a particular galvanic cell. So, when it is suitably coupled, the two half cells, one I told about the oxidation half cell and reduction half cell. So, when they are suitably coupled, so what happens? There will be tendency of the metal, that means the metal must be in contact with the solution of its own ion. That means that how zinc was in contact with zinc sulphate and copper was in contact with copper sulphate. So, if this situation arises, so there will be tendency of the metal either to get oxidized or to get reduced. So, these two processes will produce an electrical double layer at the metal and solution interface, electrical double layer. So, that electrical double layer gives rise to a potential called the electrode potential. That means, so depending upon the process going on at the particular electrode, when that electrode in contact with the solution of its own ion, that so we call it in the oxidation potential or we call it a reduction potential. So, it is the two types oxidation, it is either oxidation potential or it is reduction potential. So, how can you define electrode potential? So, in general, electrode potential is the tendency of a metal to either lose or gain electron when in contact with the solution of its own ion, solution of its in contact. So, in that process, an electrical double layer, electrical double layer or EDL is formed at the interface. Suppose I will take zinc. So, in case of zinc strip, what happens? Suppose it is zinc sulphate and this is zinc. So, the electrons will be here, the zinc ions, the positive zinc ions will be here, this will be zinc ion. So, this is an anodic compartment in fact. So, this is suppose an anode, zinc is made anode. So, this is an anode is always a negative electrode, it is a negative electrode, anode is called a negative electrode here. So, at the interface you see this is the solution side and this is the metal side. So, the two layers of charges are formed. So, this is responsible for the potential called the electrode potential. So, okay. So, electrode potential is the tendency of an electrode either to lose or gain electron while in contact with a solution of its own ions. So, in the presence of electrical double layer gives rise to electrode potential. So, it is very important. So, there are we know there are two electrode potentials we make use. So, one is your oxidation potential, another is reduction potential. So, both are in equal magnitudes, but opposite in sign. For example, the E0 reduction potential, suppose zinc 2 plus zinc is equal to minus 0.76 volt, minus 0.7. So, this is you see this is reduction potential because you see this sense of writing this is plus 2 and this is 0, this stands for reduction. So, it's the oxidation potential will be of the same electrode will be written in this way, zinc 2 plus, this will just reversed and the value will be plus 0.76 volt. Similarly, for copper the reduction potential will be plus 0.34 volt and the oxidation potential will be minus 0.34 volt. They are same in magnitude, but opposite in sign. And very important point is that the electrode potential is always expressed as the reduction potential. That means, whatever if electrode potential is written somewhere in the problem, it is also you will assume that it is definitely the reduction potential. So, in the next slide we shall go to the standard electrode potential. I have already told we can measure the standard electrode potentials by coupling an electrode suitably with a standard hydrogen electrode SHE, or we call it a normal hydrogen electrode. So, suppose we need to calculate the electrode potential for of copper. So, what we will do? So, the setup, the cell setup for this cell for calculating E0 copper 2 plus copper, that means the reduction potential. So, I have to couple it with a standard hydrogen electrode and I can get the value of this, because the standard potential of a hydrogen electrode has been arbitrarily taken as 0 volt. So, what I will do here? So, I will take platinum H2 gas at 1 atmosphere pressure, S plus 1 molar. So, this part is a SHE, standard hydrogen electrode, and when it is coupled with copper 2 plus copper solid, and copper also 1 molar, copper 2 plus 1 molar copper solid. So, this is the suitable cell for the standard. So, in the calculation we will get the value E0 zinc 2 plus this copper 2 plus copper to be plus 0.34 volt. This will be plus 0.34 volt. In fact, how can you get it? This is in fact this is E0 copper 2 plus copper minus E0 half H plus half H2, and its value is, this value is. So, when you couple this, the current flow through the voltmeter is found to be 0.34 volt, and this is arbitrarily taken as 0. This is 0.34 volt minus 0.0 volt. This come out to be 0.34 volt. So, this represents the reduction potential of copper. So, now we shall how can you calculate the EMF of cell or this? So, there is an electrochemical series, or that is also known as the electromotive series, where all the electrodes, metals and non-metals, they are arranged in the increasing order of their reduction potential values. So, it starts with lithium plus lithium, its value is minus 3.05 volt, and goes through zinc whose value is minus 0.76 volt, and in the middle it comes hydrogen, it is 0.0 volt, and then that will be copper, this will be 0.34 volt, and finally there will be fluorine. This is F minus will become F2. So, its value will be 2.87 volt. So, this is the least value of reduction potential, and this is the highest value of reduction potential. So, this is in fact F2 to F minus. So, this is known as electrochemical series. So, from this we can know the standard electrode potentials. So, all these values have been found out using your standard hydrogen electrode. So, in fact, EMF of cell is equal to E cathode minus E anode. So, or we can say take it as E anode plus E oxidation plus E reduction. So, there will be 4 ways to express the E cell. Always you take the reduction potential, it will be easier. So, E cathode to E1, it will be easier for calculations. So, you always take the reduction potentials, standard reduction potentials, to calculate the EMF of the cell. So, next we shall proceed. So, what we have told in the beginning, that the decrease in free energy of a reaction or processes occurring at the electrodes is the driving force for the production of electrical energy. So, see that part we shall go. So, that is decrease in free energy, that is your minus del G is equal to your electrical work done. So, what is electrical work done? This is charge into potential. Charge into potential. What is the charge here? Charge is NF. For n moles of electrons are passing, so the charge is, and the potential is measured in E0. So, this is, so finally this relationship del G is equal to NF minus, this is the relationship. So, for a cell to operate, the E0 always greater than 0. This implies cell operates. For the functioning of a cell, the standard EMF must be greater than 0. And now we shall proceed to the Nernst equation. Nernst equation. So, where we shall give the dependence of the cell EMF or the potential on the concentration. So, we shall start with an equation like this, del G is equal to del G plus RT ln K equilibrium. So, if we shall use that the driving force required for for a cell to operate, so we can put here minus NEF, this is equal to minus NE0F plus RT ln K equilibrium. This implies your E cell is equal to E0 cell minus RT by NF ln K equilibrium. And if I will put the values of the constants, this will come out to be E0 minus 0.0591 by n log of K equilibrium. So, this is E cell. This is a general equation, this is general Nernst equation which we shall apply to a specific electrode process, either oxidation reduction, or we can also apply it to a general process of a general process of cell reaction. So, now let us consider. So, again we shall call it the Daniell cell. Let us apply this to Daniell cell. So, Daniell cell is your zinc going as zinc 2 plus 2 electron, and copper 2 plus is gaining 2 electron becoming copper. So, if we will add it, so the overall equation will be zinc solid plus copper 2 plus, so any concentration whatever, let it be C1, and this is zinc 2 plus, let it be concentration let it be C2, and this is your C1 concentration plus your copper. So, copper solid. Now, I can apply this equation to this to get the EMF at different concentrations. So, how you can apply? So, this is E cell is equal to your E0 cell minus 0.0591. Here n is equal to 2. Why 2? Because there are 2 electrons are exchanged in the process of oxidation and reduction. So, this is of log of zinc 2 plus concentration divided by copper 2 plus concentration. So, knowing these concentrations C1 and C2, these values, so and this is a standard value, you know. So, for this is 1.10 volt. So, you can compute the EMF of cell at different concentrations. So, in this way we completed the chapter electrochemistry. I hope you can well understand this. Thank you all.